Hi, welcome back to Structural Analysis Made Fun and Easy. This is Analysis of Statically Determinate Frameworks Part 2, Deflections, Chapter 3. So I've started work on one of the sample problems. So this is a run through of his example in the book Linear Analysis of Frameworks by Grave Smith. So this is example 3.1. Just a simple pin jointed framework with 2 point loads on it. 3 meter grid again. So example 3.1. Suppose we require the particular displacements D1 of the pin jointed framework analysed in example 2.23, see the previous video, and also shown in figure 3.4, so that's the same one again. All the members of the framework are of steel with Young's modulus 200 giganewton per metre squared. I don't know why he's putting Young's modulus. Why can't he just say 200? Why can't he just put it in newtons and millimetres? The cross-sectional area in square millimetres are shown in the figure. So we got cross-sectional area ABC 500 millimetres squared, CEF 750 millimetres squared. 1, 2, 3, 4, 5, A, B, C, D, E, F. So A, B, so the top ones, A, B, D. The top sort of T section, A, B, and the D is 500 millimetres squared. C, E, and F are 750 millimetres squared. Maybe he's just doing this to make, just so that people can practice the areas. In the virtual work equation of 3.13, we shall take as the unstarred displacements of the compatible displacement system the actual structural displacements of the pin jointed framework under the loading in figure 3.4 and the corresponding member extensions. Then, in order to determine D1, we choose for the equilibrium force system a single unit vertical force acting on the structure at joint 3 in the required direction D1. The corresponding internal forces we shall call N1. This lowercase notation is used throughout the text to represent equilibrium force due to unit forces, and the asterisk can therefore be dropped as an unnecessary complication. The subscript 1 indicates which displacements is being sought. Thus, in the virtual work equation 3.13, P1 star equals 1, P2 star equals P2, P3 star equals ... equals P asterisk N, equals 0, N asterisk equals N1, and the equation reduces to 1 times D1 equals the sum to M of N1 displacement M. Right. This is an explicit expression for the required displacements D1. In calculating the right-hand side of 3.15, the member summation is carried out in tabular form. So note that forces N1 corresponding to a unit force are considered to be dimensionless. Note that forces N1 corresponding to a unit force are considered to be dimensionless, i.e. Newton divided by Newton. This is shown in table 3.1. That's on the next page. Wait a second. For conciseness in this and all subsequent tables, the appropriate basic values of the SI system, namely combinations of newtons and meters, are used for all quantities, unless otherwise stated. Numbers are presented in engineering notation and should be multiplied by the appropriate multiples of 10 to the power 3, shown in the left, 1,000 that is, shown in the left-hand column. The extension of the members delta are calculated from the axial forces which were determined in example 2.23 by the methods of joints. These are shown in figure 3.5a, where the arrows in the member indicate the direction of the internal forces applied on the joints. The forces M1 are also calculated by the method of joints and are shown in figure 3.5b. For clarity, the hypothetical unit forces of the equilibrium force system will be distinguished in figures from the actual forces of the framework by drawing them with medium arrows. Carrying out the summation horizontally across the table then gives D1 equals 2.71 millimeters. The analysis can be repeated for other deflections, and a general form of 3.15 is DI equals sum to m of Ni delta m 3.16, where Ni are the axial forces due to Pi equals 1, Pj equals 0, J naught equals I. That's for D2 in figure 3.4. We load the structure with a unit vertical force at joint 4 in the required vertical direction and reanalyze by the method of joints to give N2 as figure 3.5. Oh, C, that's C. Their calculations are included in table 3.1, giving D2 equals 1.9 millimeters. So this is N, fully loaded structure. Then he's done equilibrium of joints, so we've got a unit load of 5 and 10 kilonewtons. So that gives you 2510 minus 21.20. Oh yeah, which one? Oh, so the other thing to remember is he's put tension is positive, so 25 and 10 are positive forces. Oh, and 2, 4 is also 10, which is, that's tension, yeah. And then the other ones are minus 21.21, minus 10, and minus 14.14. So here we got a junction, a load of 4, 2, 1, 1.41, minus 1, 1, 1. So in figure B, we got 2, 1. Oh, sorry, that in figure. So this is figure B is N1. The diagram for N1, which is a unit. Well, I thought it was a unit load of 1 kilonewtons, but he said it's dimensional, so that's 1. 1 vertical downwards. And then you got, so tension of 2, tension of 1, 1.4, minus 1.41, compression, minus 1, compression, 1 tension, minus 1.41, compression, 2 is 1, 0. Oh, sorry, N2 is apply that I thought it was apply 1, force of 1 downwards, and then find the forces. So that's 0, 0, 1, 1, minus 1.41. There's 3 redundant members there. And that is unit force. Oh, yeah. Yeah. A unit horizontal force of 1 at joint. There, that's 1, 1, 1, and 3. So, oh, you turn over. So here's the table. I think, like, oh, so with calculations, for example, 3.1. So we've got member A, B, C, D, E, F. So the length, that's in meters. L of length, member A is 3 meters, B is 3 meters, C is 4.24 meters, D is 3 meters, E is 4.24 meters, F is 3 meters. A, area, oh. Area, is that supposed to be in meters? It's very confusing because he's got the units in different. Why is that? Shouldn't that be in millimeters? And then A should be in millimeters squared, but it's times 10 to the minus 6. So it's 500 millimeters squared divided by 1,000 to give you meters squared. So A in meters squared times 10 to the minus 6 is 500. N is 10 to the power of 3. So N, oh yeah, 25 kilonewtons. So that would be newtons. So that's times 1,000. So you've got 3. So the length is 3 meters, 3,000 millimeters, 3 meters, 3,000 millimeters, 4.24 meters, 4.240 millimeters, 4.243. A in meters squared, 500 times 10 to the minus 6, 500, 750, 500, 750, 750. N, 10 to the power of 3, 25, 10, minus 14.14, 10, minus 21.21, minus 10. Delta, n to the power of 3. Oh, so delta is, it doesn't really say on that other thing, but delta equals to NA divided by EL. So delta is 0.75. So that's N, that's 25,25000. Oh, or Has he done 10 to the minus 3? I'm not sure about these units that he's using. But anyway, NA is 25 times 500 divided by 3 times 205, because A is NA over LE. That gives you the delta value of 0.75, 0.3, minus 0.4. So it's a minus for compression, because that means it's, oh yeah, its compression is like it's not an extension, isn't it? So if the member's in compression, it's not extending. 510, 0.3. So the delta values are 0.75, 0.3, 0.4, 0.3, minus 0.6, and minus 0.2. N1 is, N1 is just the unit, isn't it? The unit. I don't know about the units, but I thought it was the forces in the members due to M1, which was a vertical force downward. So it's 2, 1, minus 4, 1.411, 1.41 minus 1. Then N1 delta is obviously 0.75 times 2 is 1.5. 0.3 times 1 is 0.3. 0.4 times 1.45 is 0.57. 0.3 times 1 is 0.3. 0.6 times 1.41 is 0.85. 0.2 times 1 is 0.2. And then so you total that up. So 1.5 plus 0.3 plus 0.3, say, that gives you 2.1 plus, isn't it 2.1 plus 85 is 2.95. Oh yeah, plus 2.95, what did I say? 2.95 plus 0.2 plus 0.57. Oh yeah, that's it. Because 0.2 plus 0.57 is 0.77. That takes it up to 3.7 millimeters. He's put that as meters, but oh yeah, he's put 10 to the power of 3 there. So it's that's the sum is meters times 10 to the power of 3, so that's millimeters then. 3.71 millimeters. And the same thing with N2, 1001 minus 1.410. N2 times delta again times 10 to the power of 3 meters. And you add them up and you got 1.9. And then you got N3, 11000. N3 delta 0.75.3. And then you get that. So you got D1 is 3.71. D3 is 1.05. 1.05 and 3.71. And you got 3.86. So, oh yeah, because you got, if you want 3.86 equals to the square root of 3.71 squared plus 1.05 millimeters squared. Or then he's worked out the angle as well. You can work out that, isn't it? Because tan the alpha equals 1.05 divided by 3.75, and then that gives you arctan the alpha gives you that in the smaller angle, and then 90 minus that smaller angle is 74.2. And so the total deflection is the resultant deflection is 3.86 at 74.2 from the horizontal. It's a bit. I do another example. I work through my example because this is fairly complicated because it's just confusing with the units as well. Don't know why he's put it in. He's put it in newtons and meters. Be easier just to put it in millimeters, because then you don't need the times 10 to the power of 6, and the n. You still have n to the 3, but you could just put 25,000. And then the delta would be, is that supposed to be millimeters? Yes, it would be millimeters. Because he said N1 was dimensionless. So M1 delta is millimeters again. It is important to note that as a result of the definition of external work, the unit force method isolates on the left-hand side of the equation of work of virtual work, the component of the total deflection of the point in the direction of unit force. Thus, it is not implied that the deflection of joint 3 of the framework is actually vertical. Thus, it is not implied that the deflection of joint 3 of the framework is actually vertical. If we do need to calculate the total deflection of the point, it is necessary to determine the components in 2 orthogonal directions. Thus, in the case of total deflections of joint 3, we should also need to calculate the horizontal deflection D3, shown in figure 3.4. That's that. Oh, sorry, 3.4. This calculation is carried out in table 3.1 using the axial forces N3 corresponding to the unit horizontal loads of joint 3 given in figure 3.5D. Thus D3 equals 1.05. The total deflection of joint 3 is then the vector sum of D1 and D3 being a displacement of magnitude 3.86 millimeters directed at 74.2 degrees to the horizontal. So he's done there's some calculations done that's not shown here. And oh yeah, because he hasn't clearly shown the delta value is NA over EL. I think it would help if that was put in. So I do an additional video on this one, just show that that's what we need to do. LAN delta. Because then you got what's it again? NA divided by L times E Young's modulus. So it's basically the extension, isn't it? Because E is stress over strain. So I do an addendum video to this video, but this is like straight out of the textbook. So can't blame me if it's hard to understand, because I did find it hard to understand. Some of it's missing, in my opinion. The delta values and the units are just confusing. I don't see the point in why put that 10. What's the point? It's just annoying. It's just saying delta is in meters when it's clearly going to be in millimeters. It's just stupid. And then putting E, he's giving you E and giganewtons per meter squared instead of just putting it in newtons per millimeter. It's just, that's another annoying. It's just annoying. But hopefully you still found this video useful. I just don't see the point in doing that. It's just stupid, if you ask me. Hopefully you still found the video. Oh, so just a recap of it over there. So that in the table, he's got because he's got the forces. So and the diagram for M is in kilonewtons, but the other ones, he's saying they're unitless. 1, 1, and 1, N1, N2, and 3. It's a bit confusing, if you ask me. Oh, anyways, hopefully you found this useful, and please leave any comments. Please like the video. Please subscribe to the channel so then I can do the rest of the chapter, beginning of the chapter. Thanks for watching. See you in the next video. Thanks.